So that is a result we would get if we were doing this in a vacuum, but we know that the experiment was not done in a vacuum. It was done with a fiber optic cable. So let's try to account for that using a classical intuitive approach and see if that works or not. So starting with the red path, the light comes out of here and then it goes in this direction around the racetrack. This little blue arrow here is indicating the motion of the fiber optic cable, and we can see that the light is traveling in the opposite direction from the fiber optic cable. So the light is traveling against the flow of the glass. And intuitively, we might expect then that that's kind of like a boat on a river. If a boat in still water moves at a certain speed, then if you're moving against the current, we would have to subtract the current speed from that to get the speed in the red direction. Speed of light through a moving fiber optic cable in the red direction is the speed of light in the cable fixed minus the speed of the cable. And I'll emphasize that this is what we expect it to be, but we kind of know that that's not correct. And we're just going to run with it for now and see where this leads us and see if we get any insight from that. Also, I'm getting a little tired of writing c divided by n all the time, so I'm just going to write c sub n. That's a little smaller. And so the c sub n is the speed of light through a non-moving fiber optic cable. So in the red direction, we have the speed is cn minus v. And in the green direction, see in the green direction, the light is moving with the cable. So now we're steaming our boat downstream. And so the green speed should be c sub n plus the velocity of the cable. For the red beam, there'll be a little extra time as we go around the loop and a little short time because the gyro is moving. Okay, let's try to count up that time as a total amount of time and say how long is it going to take the light beam to start at the fiber optic gyro, go around the racetrack, cut out a little early, and then hit back to the fiber optic gyro. So the entire time, the light is flowing in the red direction against the flow. And so if we count up the entire distance, the path distance the red beam has to go, and divide that by the speed of light in the red direction, that'll get us how long it takes red to make the trip. Okay, there's a note here. The t in VT. What t is this? We needed to ensure, we agreed before that we need to ensure that this t and this t are the same. And since I'm starting with red on this slide, I'm doing red first this time, I'm just going to say, let's use red time. We'll use the red time, boom, 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 and then we'll say the fiber optic gyro moves by that same amount of time for the green so that we can compare apples to apples and get these distances to be the same, because we do want to make sure between the fiber optic gyro started moving from there and it ended up there. That's the amount of time that's the same. We don't really care how long ago the green light came out for that purpose. We're going to use that to calculate how long the green light has been going around the track. I'm going to take the red's time and plug that in there, and we'll see why that's kind of convenient here as we do it. So the total path length that the red beam goes is the full loop, the full length minus this little thingy here. The red one does not have to do this little piece here. And what is that piece? It is 1 VT. So 1 VT, and we said let's just use T red. So that's the total path for red and the speed of red. Speed of red is the speed of light in glass minus the V. Okay, I'm going to just do some math and come out with the equation 6. And because I happen to choose T red there, it comes out easy as L over speed of light in glass. Okay, let's do the same thing for green. Same thing for green now, path green divided by speed green. And the path of green. Path of green is one full loop, or it's, the whole loop, plus a VT, plus one extra one of those. So we're going to put L plus VT, and the speed of the green beam is the speed of glass plus the velocity V. And we agreed we're going to use the same amount of time because we want to know how much shift there is after that amount of time. And so the T red here from this previous equation, we're just going to plug that right in there. And then we do a little bit of mathing. And lo and behold, T green comes out like so. They're identical. And so what does that tell us? That there should be no fringe shift. So using classical intuition, this experiment should not generate any fringe shift. However, we saw experimentally that it does create a fringe shift. This is a proof by contradiction, right? The Wang experiment literally proves that our classical intuition method was incorrect. That was wrong. Our intuition about the speed of light in moving glass was wrong. And in fact, I had forgotten this myself, and I only rediscovered this by digging into why this came out so horribly wrong. I discovered the Fizeau experiment in 1851 had literally measured the speed of light in moving mediums to not be what we expected, which was we expected it was c over n plus v, but that's not what it is. It's c over n plus v times this quantity. I'm going to say that's simply not intuitive, but that's what it was measured to be. So perhaps we should redo this whole thing using the speed of light as we understand it's supposed to be and see if that works out for us. But before we do, I wanted to show this, and I wanted to use it to emphasize that intuition cannot be trusted. Intuition is not always going to be correct. That's literally the point of doing science, is to find out whether your first guess, your feelings about how things should work are right or not. And we have found in this case, and Wang supports us, as Fizeau found many, many years ago, that is not how light moves through a moving medium. That in fact, we have to account for this term, and maybe we'll explore that next.